last of the examinable topics, we'll look at deadline electronic analysis, the first 18 pages of that paper I referred you to last week, and dynamic scheduling techniques, where we've got a lecture that the soundtrack mysteriously disappeared from that, probably a blessing. But it'll only take about 10 to 15 minutes for me to walk you through that anyway. And then sometime next week I'll re-record that and put it back there anyway for those of you who might be subject to punishment, whether you want to take a dose of it, yourself. I noticed a distinct lack of enthusiasm for going through tutorial problems last week. That's fine. What we'll do is we'll stick to the plan here and have a look at the extent rate electronic analysis tutorial problems. There's only a couple of them. And then next week, of course, there'll be no new material. What I do recommend is that we get organised before the class with all the tutorial problems that you either haven't done or don't understand, or think I've got the answer wrong to, or whatever. Bring those, and then we'll deal with them in the class, so that by the end of next week's session, everyone has had a good opportunity to get grips with all the tutorial problems. That is the ones out of these two documents here. Well, that document there and the answers there. I think once we've done that, that's it. You can finish off the assignment. I've been saying to people that probably getting it submitted by midnight Sunday the 7th would probably be a good idea, because then I can start marking it straight away the following week. What I really want to do, I'm not too aimless out of all of that, what I really want to do though, and this is important, is I want plenty of time to get all the marking done before the exam, which I think is on, when is it, 15th or something like that? Yeah. It is 15th? Yeah. All right, so I want to get all the marking done as early as possible in the first, as early as possible after Monday the 9th. I want to have it all done by, Monday the 8th. I want to have it all done by Wednesday night, basically. So get your assignment submissions to me as early as you can that week, and then I'm going to get it all marked so that there's plenty of time for you to check the grade book and know what you've got before the exam starts. That all make sense? Since there's not very many of us enrolled in the subject, we don't have to get too dynamic about submission times and stuff like that. It's probably better for you to have a little bit of extra time to do a proper submission rather than just get it lodged by some arbitrary point in time. And if that works for you, then that'll work for me. Like I say, I just want to get all the marking done by, when did I say? Wednesday the 10th. Yeah, I want to have it all done by then. Okay, so that takes us to, yes, this one. This is the paper I was telling you about last week. We're going to have a bit of a look through now on the deadline monotonic scheduling. This is a generalisation of rate monotonic, where we've got pre-period deadlines now by a fixed amount. The task is a deadline that precedes the period. Of course, like I say, this is a generalisation in comparison to rate monotonic, where with rate monotonic we're assuming that deadlines are coinciding with periods. Not any time before that, we're just assuming that they're coinciding with periods, full stop. But you can imagine there will be plenty of scenarios whereby the system that we're building our real-time system to interact with will have pre-period deadlines attached to it. And this is how we're going to deal with those. I don't know whether you remember, but when we watched the video, Ruth was talking about two techniques for dealing with modelling pre-period deadlines. One where she was saying that you can work out what the pre-period deadline is, or have that given to you by the external environment, of course, and then that amount of time you just add as execution time. So an artificially extended execution time for the process. That's one hack. The other way she mentioned on doing it is one that we're not going to worry about either, because here we've got a stricter and much more logical approach to dealing with these pre-period deadlines. So we'll ignore her approaches, which are a bit ad hoc, and look at the ones that are in this paper instead. So this is a reasonably old paper, but useful nevertheless. And one of the things that makes it a little bit more interesting than many academic papers is he's actually gone to the trouble of providing a few numerical examples. Usually, with most academic papers, someone will say, this is the way we've worked out how you can do such and such, and they write a paper about it, and that's it. The real demonstrations are left as an exercise for the reader. But this time around, we've got Dr. Wardsley's taken gone the extra yard and included some numerical examples which are useful to us. So we'll have a look at those. That's basically what we're going to do. He starts by providing a good recap into the analysis of real-time systems, including rate monotonic, which we already know about. So he describes the rate monotonic scheduling algorithm there. Where is this about now? So there's our on the left-hand side, that's our CPU utilisation, the actual CPU utilisation, the amount of time the process does the XD instructions. And that quantity on the right-hand side is a theoretical upper bound that you have derived for us. And he mentions that that test is sufficient but not necessary, which again we already know. And he goes on to provide theorem 2 by Mahofsky, Shah and Dean there, which we also know. So it's not new material that, but it probably makes sense to have a bit of a read through it again at some point in time. Note down the bottom here, he's introduced a couple of mathematical operators. And I mentioned before, these things are not brackets. This operator here indicates the ceiling of x, and this operator here indicates the floor. The way in which we interpret those operators is the ceiling operator rounds a number towards plus infinity, and the floor operator rounds a number towards minus infinity. Okay? So, what would be the ceiling of 3.1? We've rounded towards plus infinity. So the ceiling of 3.1 is 4. Alright. What would be the ceiling of 5.9? 6. Yeah. What would be the floor of minus 2.1? Minus 3. Thank you. That's right. Round towards minus infinity with the floor operator. So rounding towards plus infinity, rounding towards minus infinity, because we'll be making heavy use of those. Okay, he introduces the constraint for deadline monotonic scheduling here. Now our computation time has got to be less than or equal to a deadline, which is less than or equal to a period. In the opinion of Hunt itself, that really should be less than there, not less than or equal to. But it doesn't matter, we'll let him off. In fact, he's made a couple of mistakes in this paper, but, well, that happens. And we can deal with that. So now we've got a computation time, which we must be less than or equal to a deadline, where the deadline is less than the period. And of course, in deadline on some assignment, we can imagine the priorities now being ordered inversely with respect to the deadlines, not the periods. So the process with the shortest deadline has the highest priority, not the shortest period, shortest deadline. Now often those two might coincide, but strictly speaking, we're now going to order the processes in terms of their deadlines and associate monotonically priorities with deadlines, not periods. Okay, so all of that's pretty easy, I think. Nothing, no headaches there, I don't think so far. Right, well, the way in which he embarks on his analysis here is he looks at the schedulability of two processes, which is a good idea. He's starting out. So he's got two processes, 1 and 2, and process 1 is a higher priority than process 2 because its deadline is less than process 2's deadline. And he draws a couple of pictures. I'm not going to drag you through the derivation of it. You can have a look at that if you want, but that's not examinable. He draws a few pictures and he works out on his whiteboard what he thinks is the go. And after a couple of pages of analysis, he comes up with this expression here, which he's called equation 5. Equation 5 is actually made up of this bit and this stuff, of course. So what we've got here in equation 5 is for two processes only. We've got a test to see whether or not those processes will meet their deadlines, where the deadlines precede the periods. And the information that we've got here, or the quantities that we've got in this test, are C, the computation time for the task, obviously, just the same nomenclature as we've used before. D is the deadline for the task, where the deadline is less than the period, of course. And this new quantity I over here, he calls an interference factor. Basically, that is pretty much a preemption factor. So that will be influenced by higher priority processes that preempt the particular task in question. He calls it an interference factor, which is fine. That's what we'll call it too. But essentially, its nature is of a preemption factor. Remember the preemption factors we saw last week. All right. Well, this is his test. Obviously, for the highest quantity, the highest priority process, if this interference factor thing acts like a preemption factor, then it can't be preempted by any other high priority processes, so its interference factor should be 0. That's the case for the highest priority process. Right? So that kind of makes sense, given our understanding of what the preemption factor actually models. So the interference factor 1, I sub 1, is always 0, always. And of course that means the test for schedulability for the highest priority task is the execution time less than the deadline. So that's the trivial test. Pretty obviously. That's all there is to it for the highest priority task. We do that in our heads. However, the expression for the interference factor for the second highest task, highest priority task, in this case remember we're only dealing with 2, start off with the case of 2 tasks. There is the expression for the interference factor. So you say the interference factor, in brackets, preemption factor, is the deadline for task 2 divided by the period for task 1. Take the ceiling of that, multiply it by the execution time for task 1. And that will be the interference factor that task 2 experiences as task 1 preempts it. So that's the test, nice and simple. What he's done, again, I reiterate, he's done the right thing and provided for the few generic examples. Here they are, nice and simple. 2 tasks only, and we can see that their deadlines precede their periods, just as we would expect, since we know we're dealing with deadline monotonic scheduling now. So deadlines preceding the periods. We're going to use equation 5 to see if these 2 tasks will always meet their pre-period deadlines, even in the worst case scenario when they all want to run at once. Well, for the highest priority task, remember, I1 is always 0, so we've simply got execution time divided by deadline. We need that to be less than 1, which it is in this case. And then we've got the interference factor for task 2 to evaluate in testing the schedulability for task 2. So we put the execution time for task 2 divided by the deadline for task 2, interference factor for task 2 divided by the deadline for task 2. We evaluate the interference factor for task 2. And it is, as we saw over here, deadline for task 2 divided by period for task 1, the ceiling of that multiplied by execution time for task 1. So deadline for task 2 divided by period for task 1, 10 over 5 is 2. What's the ceiling of 2? 2. 2 multiplied by the execution time for task 1, which is 2, is 4. So there's our interference factor, and we can see that the inequality is satisfied, so good, the tasks will meet their deadlines. Both of them will. Nice and easy. He's written down here, though, the construction of I2 is sufficient but not necessary. Now, where have we heard that before? Newton-Layton's theorem number 1, haven't we? Yeah, sufficient but not necessary. If we plug in the numbers and the inequality is satisfied, good. If we plug in the numbers and the inequality is not satisfied, it doesn't necessarily mean bad. He's written here, the following example shows that. Consider the effect of increasing D2 to 11. This should not affect the schedulability of the system. And how can he say that with so much reassurance? He's just modified the example that we worked through and said this should still work. How can he say that? to the effect of increasing D2 to 11, this should not affect the schedulability of the system. Why is that statement justifiable? Sorry, mate? Yeah. Yeah, we just demonstrated that with a deadline for class 2 of 10, right, it was able to meet its deadline. So if we increase the deadline from 10 to 11, we haven't made the constraints any tighter, have we? We've actually relaxed them a bit. So he's quite right. Increasing D2 from 10 to 11 should not affect the schedulability of the system. We've actually made it easier. We've widened the goalposts. However, when we plug the numbers in here, we can see we've got the ceiling of 11 over 5, which is now 3, times 2 is 6. And so we end up with the inequality here indicating that the tasks may not be schedulable. However, we know that they should be. So he's right. It means that his expression for the interference factor for task 2 is not quite right. It's sufficient but not necessary. So what he does is he goes back to the drawing board and has a closer look at the nature of the modelling of the interference factor. And after a couple more pages of grunting and swearing, he comes up with this. Yeah. All right. So there's the expression for the schedulability of 2 tasks, just as it was before. The only thing that's changed is the expression for the interference factor, which we just acknowledged was sufficient but not necessary. And so this is what he's saying is a better form for modelling the interference factor. This one's more accurate. But just as we might expect, it also requires a bit more accurate. So he's saying the schedulability of this test now, equation 7, is sufficient for 2 processes. He wants to demonstrate this now. So the revised version of the interference factor, the more precise version, is the one which he wants to test. And so he does. We go back to the example that we looked at, where the deadline for task 2 was 10, and we extended it to 11. And we want to test that now with this more precise version of the interference factor and see if it works. And so we plug in all the numbers. 11 minus 3 is 8 over 5. The floor of 8 over 5 is 1. Yeah. 1 plus 1 is 2 times 2 is 4. So that's the first term there. Just evaluated that bit there. That's 4. We've got this term here again. 11 minus 3 is 8 over 5 is a number between 1 and 2. So the floor of that is 1. Plus 1 is 2. 11 over 5 is a number between 2 and 3, so the ceiling of that is 3. 3 minus 2 is 1. 1 times the minimum of 2 and this term over here. We've got the floor of 11 over 5. What's the floor of 11 over 5? (11 over 5 is a number between 2 and 3, so the floor of that is 2. 2 times 5 is 10. 11 minus 10 is 1. The minimum of 2 and 1 is 1. 1 times 1 is 1. So there's our new interference factor with the more precise expression. It's 5. We calculated before, we thought it was 6. So we've got a more precise version of the interference factor now, 5. And that means that our test now is complete. We've got this more precise version of the interference factor, and it's giving us the right answers. Okay. So he's got down here a note that the order of computational complexity is significantly different, and we might expect that. The imprecise version, in other words, the simpler form for the interference factor, this one up here, of course, is easier for us to calculate. Order n in computational complexity, but the more complicated version is order n squared. And that is probably something that we would have suspected. A trade-off exists between accuracy and computation complexity. Yes, just as we know. That's how the universe works. All right. So that's the case for two processes, but that isn't going to get us very far in any real engineering context. So he's extended this to have a look at the stretchability of many processes. So now we've got an arbitrary number of processes. He wants to generalise equations 5 and 7, basically. So back to the drawing board, Pete's more squiggly, which he's left out. And he's come up with, again, two more tests for the schedulability of tasks with deadline monotonic scheduling, with pre-period deadlines. And there's the test there with the imprecise expression of the interference factor. And we'll test that. So this time around we've got three tasks. T1, T2, T3. Pre-period deadlines every time again. Let's see how equation 8 here can be used to evaluate the schedulability of this set of tasks. Again, the interference factor for task 1 is always 0, so simply 2 over 3 is less than or equal to 1. Yes, it is. For task 2, we've got an interference factor, and we're plugging the I equals 1, I equals 2 here, and we're summing between j equals 1 and 2 minus 1, which is 1 here. So there's our expression for the interference factor for task 2. There's our expression for the interference factor for task 3. The deadline for task 3 over the period of task 1 multiplied, I'll take the ceiling of that, multiplied by the execution time for task 1. And the deadline for task in question again divided by a period for task 2. Take the ceiling of that, multiplied by the computation time for task 2. Plug in the numbers, all the inequalities are satisfied, so the tasks will meet their deadlines. And he does the same trick as he did before. He extended the deadline for one of the tasks, the lowest priority one, again noting that this should not affect the schedulability of the system, but when we plug the numbers in, we can see that that imprecise version of the interference factor is again misleading us. So, of course, the last step is to derive this expression here, which is the more precise modelling, the more precise characterisation of the interference factor for an arbitrary number of tasks. And we finish off by applying that to this last set of problems here, where we've extended the deadline for task 3 from 10 to 11. The only problem is, this is where he makes one of his arithmetic mistakes here. He ends up with, there's the test for task 1, again, interference factor for task 1 is always 0. There's the interference factor for task 2, that's not onerous, and it's all correct. So 6 minus 3 is 3, 3 over 5 is a number between 0 and 1. The floor of that is 0. 0 plus 1 is 1, times 2 is 2. 6 over 5, the ceiling of that is 2. Yep, 2 minus, we just calculated that, that's all 1. 2 minus 1 is 1, times the minimum of 2, and this stuff over here, well, we've got the floor of 6 over 5, that's 1. Yes, thank you. That's right. Times 5. No, wait a minute. The floor of 6 over 5 is 1. Yes. 1 times 5 is 5. 6 minus 5 is 1. The minimum of 2 and 1 is 1. That's all right. That's, yep. All right, so remembering that the floor and ceiling operators are not brackets. Of course. So there's our interference factor for task 2. It's 3, using the more precise expression. The problem is, when he plugs these numbers in down here, he makes two mistakes, unfortunately. The good news is the mistakes cancel one another out. So if you're going to make mistakes, this is the way to do it, folks. He's placed here, this should be the computation time for task 3. Right? Computation time for task 3. However, what he's actually done is he's put 3 down there, whereas up here the computation time for task 3 is 4. So he's made a mistake. That 3 should be a 4. That 3 there should be a 4. So that's going to change things just a bit. And then the other problem is he's written down the wrong time for the period for task 2. He's written down 10. So everywhere we see the period for task 2, he's written 10. So there's T2, 10. However, the deadline for task 2 is actually 15. He's made 2 mistakes. I'd like to say this is the way to make mistakes. So that 3 should be a 4, and all of these 10s here should be 15s, which is really going to change the relationship of the results from the forward tuning operators. So when we plug all those in, we actually get 7 there, not 8. So we get 4 plus 7 over 11 is 1. So the answer's still okay, it's just that there's 2 arithmetic errors in there, which I don't want you to be confused about later on. So make either a mental note or better still, an electronic or a physical note of that now, so don't get confused later. Alright, and then double bills. As far as we're concerned, those are useful results. Naturally, you won't be expected to commit those expressions to memory. They'll be quoted in the exam paper. All you need to do is know how to apply them, like this. And after we've done a couple of tutorial problems next week, as well as these ones here, we've done here and now, of course, we'll do a couple of tutorial problems next week. I don't think we'll have too much trouble. The rest of this paper is actually useful stuff too, but maybe we'll leave that for a postgraduate course sometime. So don't worry about the rest of that. So what do we get out of this? There's a good recap of information we already know about the rate monotonic scheduling scheme in the introductory part of the paper. But then he introduces a test of the schedulability of tasks with pre-period deadlines using a new quantity called the interference factor. And he derives that with 2 tasks and demonstrates that the expression for modelling the interference factor is sufficient but not necessary. So he improves upon that by creating a more precise. This one's still not actually exact. That's not exact. It's more precise, and it'll do us. So a more complicated but more precise expression there. And then that, of course, led him to the specification for the general case of an arbitrary number of processes. In the example we looked at had 3. So the test for schedulability for an arbitrary number of processes would be imprecise, the not quite so precise interference factor there, and of course the more precise version down here. There we are, equation 9. So fortunately, this analysis, even though it looks quite different, it parallels the rate monotonic stuff that we've looked at, because we've got an easy to apply yet sufficient but not necessary condition, conservative form of analysis to apply, and if that works, then we stop. If it doesn't tell us everything we need to know, we have to resort to the slightly more computationally intensive versions. So, who's got questions? Yes, mate.
What's the upside down capital A?
That is for every.
Oh, thank you.
No, sorry. Yes, for every. For every I.
Thank you.
Yes. Yeah, for every I, where I is between 1 and n. Yes. There exists a factor from uppercase D. Something to get mixed up. Okay. Yeah, any other questions? All right, well, like I say, we've got a couple of easy tutorial problems to do on that. yes, that'll take care of them. What we want to do now, or we might want to, what we will do is we'll have a quick look at dynamic scheduling techniques, and then that's the last of our examinable topics. Now, these slides were put together some time ago for a slightly different audience, and so a lot of this stuff I'm going to skip over to start with because it tells people, it assumes a different audience to us, and it recaps a lot of things that we already know about. And so you can read through that. There's nothing magical in any of this. This is not new information. It's just recapping stuff. We looked at that last week. We know what the drawbacks are with dynamic scheduling policies as opposed to static ones. Talked about that before. This is where it starts getting a bit more interesting. This slide's important because when we looked at homework problems 1 and 2 last week, we found out about priority inversion, didn't we? And how do we define, in a nice plain English sentence, what priority inversion is? Yeah, it's when we've got a low priority task executing when a high priority one should be. That's right. Right, that's priority inversion. And what sort of things did we see last week can cause priority inversion? Well, everything was going nice and straightforward until we started modifying some of those problems last week with interrupt service routines being present. And non-interruptible, non-preemptible sections of code. So those types of programming features were the things that introduced blocking factors. And remember, blocking factors have an impact upwards in the chain of processes. So a task which presented a blocking factor adversely impacted the schedulability of all the higher priority tasks above it, not the lower priority tasks below it. And that was the problem. And so what do we do with these blocking factors last week? Well, we worked out what they were, and then we simply attempted to see whether or not they can still be accommodated. So we had task execution factors, any preemption factors for higher priority tasks, and the blocking factors. And we're adding all of those up and just checking to see whether or not they were less than the theoretical upper bound on processor utilization, the U of N. That's what we were doing. We were quantifying the blocking factors and trying to budget for them, which is all we could do. However, this stuff here, the stuff we're going to look at now, and this is the reason why we're going to be doing it, these actually are designed to reduce the lengths of the blocking factors. So we're getting cleverer still. Not only are we identifying these blocking factors, quantifying them, and then seeing whether or not we can accommodate them and get the work done that we're supposed to get done. Not only are we able to do that, that's the stuff we looked at last week, the extended version of Theorem 1, but now, with these fancy techniques we're looking at here, we're actually going to discover ways in which the lengths of the blocking factors can be reduced, if not eliminated. So, here's an example of priority inversion to start with. We're going to look at two techniques, two dynamic scheduling techniques that reduce the severity of this blocking factor here, and the techniques that we're going to look at are called priority inheritance and the immediate priority sealing protocol. There are only two techniques. There are a few others. There's also a delayed priority inheritance protocol too. But I'll show you these two because they're the most popular ones. And proper real-time operating systems like Unix actually knows about priority inheritance. I'm not sure about the sealing protocol, but certainly they've got system calls in there that deal with priority inheritance. And so this stuff isn't just academic hand waving. It has found its way into proper mainstream real-time operating systems. Anyway, I'll show you that later. Have a look at this example first. It differs from the examples we've looked at in the past because it's not attempting to show the worst case scenario when all the tasks start simultaneously at time t equals 0. Right? So that's where this diagram differs from the others we looked at last week. We've still got highest priority process at the top. We always do that. Then next highest, then next highest, then next highest. And it doesn't matter now whether we're talking about rate or deadline monotonic scheduling. Doesn't matter. Let's just keep it simple and talk about rate monotonic scheduling. So we'll assume that these tasks are being scheduled rate monotonically. So task D is the highest priority task at the top, and it's got the shortest period. Then C, then B, then A. However, on this particular occasion, at time t equals 0, none of the higher priority tasks want to run. So the triggering event for them hasn't occurred. We're not looking, in this case, at the worst case scenario where they all want to start at once. We're just looking at some possible hypothetical phasing of the processes. So we've got here the lowest priority process, it wants to run, and because there's no other process running, it does run. So there's this little green block of time here, well, it's showing that it's executed. There's a key down the bottom. So task A is running. Task A needs a particular resource called Q, right? Whatever resource Q is. It might be a hardware device, it might be a memory variable, it might be some shared memory, whatever it is. It needs to get access to that resource, and it needs exclusive access to it. And so in the source code, what would we see happening there? Semaphore, did someone say? Yeah, that's right. There'll be a semaphore associated with that resource Q, whatever it is. And task A will be doing a wait operation on that semaphore, and because no one else is using it at the moment, task A, the lowest priority task in the system, it'll be successful, and it'll do the wait operation on that semaphore, and it'll get hold of resource Q, whatever Q happens to be. And so it's busy crunching away using Q, and then at time t equals 2, the triggering events for two higher priority tasks occur, C and B. So A gets preempted. C and B both want to start running at the same time, but C is higher priority than B, so C starts running. At time t equals 3, C locks a different resource. So there's some other resource in the system, and C gets hold of that. That's fine. And it uses it until time t equals 4, when the triggering event for the highest priority task, task D, takes place. So D starts to run, and it runs for 2 time units, but then at time t equals 6, we've got the problem occurring. At t equals 6, task D wants the resource that the lowest priority task A has got. And there's no way for it to get that resource. It's got to wait until task A does the signal operation on the semaphore and releases it. So there's nothing that the higher priority task D can do. It can't just go and snatch that resource. It's got to wait for it. So as soon as that happens, task G can't run any longer. As soon as it wants something it can't have, we don't leave it in the active state, do we? No, because that's called busy waiting, yeah. So we don't do that. So task G gets taken off the active queue, gets put in a block queue, and that block queue will be associated with resource Q. That's Q, not Q you're working. Right, so task D is sitting blocked. D can't run, so we resort to running the next highest priority task in the system, C. C resumes running from where it left off. It fiddles around with the other resource, B. Then it releases it. Then it continues executing, doing other stuff. Then it's finished. So it's finished its particular run. That paves the way for task B to resume. It doesn't need any of the resources, so it just does its own number crunching, whatever. And then it finishes at time t equals 10. Which means A, the lowest priority task in the system, is allowed to resume. It's still got the resource Q. It uses it until time t equals 13. And then what happens at 13? It does the signal operation on the semaphore that's associated with resource Q. And so as soon as it does that, the operating system notifies task D it doesn't need to be blocked anymore because that semaphore has just become available. So it resumes. It then locks the resource resource Q. After that, it locks resource V, and then returns V, and then finally runs and then terminates. And then when it does terminate, the lowest priority task A can resume. Now, that example looks artificial. However, what we need to remember, and Ruth mentioned this, but again, it might have been something that slipped at the time. We've only got 4 tasks being shown here. There could be any number of tasks in here, in the range where C and B are. There could be dozens of tasks. There could be hundreds of tasks in between D and A in priority order, which is, of course, only going to compound the effect of the blocking factor on the highest priority task. Real bad news. All right, so what do we do about it? Well, I mentioned before, the first technique, the simplest one, is called priority inheritance. How does this work? Well, it's quite simple. What it does is it allows the kernel to dynamically modify the priority of the process, which is doing the blocking, if it happens to be doing blocking. So here, when task A runs and locks resource Q, and then gets preempted by C and B, that happens as before. C and B are preempted at time t equals 4 by D, but at time t equals 6, that was the time when D started to become blocked. What happens at that instant is the kernel automatically elevates process A to have the same priority as process D. So A temporarily inherits the priority of process D, the one that's blocking, which means it gets to run. But as soon as it unlocks the resource and removes the blocking event, it gets its original priority back. So that priority elevation is temporary, of course, as you might expect, and occurs only during the time where it's actually doing the blocking. And that's a suitable technique to use, obviously, because what it means is A then is not preempted by C and B, as was the previous case. So they're not going to run. Where I put the mouse now, those segments of code are not going to execute because A has now a higher priority than B and C. So it runs, in fact it's got a higher priority than D even. So it runs, and as soon as it releases the resource, it gets its original priority back, so it gets preempted immediately, and the higher priority task can then be treated like a higher priority task. This priority inheritance occurs for a second time here. Right? Because task D at time t equals 10, it wants resource V, the blue one, that task C's already got. So at time 10 here, C is temporarily elevated to D's priority. And C runs until it unlocks the resource, and then, of course, gets its original priority back, and that means that the D preempts it and runs. So there's 2 instances there of priority inheritance occurring. That makes sense? Yeah. It's pretty simple, and clearly it's had an effect, a positive effect, on reducing the amount of time that D experiences blocking. And even though that picture doesn't make it look quite so dramatic, remember that if there were tens of processes in this region here between C and B, then the positive effect of applying priority inheritance would be much clearer to see. And like I mentioned, that's a real approach which is used by at least one commercial product, which I don't have anything to do with, of course. Okay, the last one, the immediate priority ceiling protocol. It's a little bit more complicated, but with the extra elaboration, of course, we get slightly better performance. What it does is it now introduces the idea of associating a priority with a resource. Now that's a bit odd, because up until now, we've been comfortable with the idea of priorities being attributes applied to processes. That's all right. We should be, that's second nature to us. But now what we've got something like, it's not exactly this, it's something like the notion of a priority being associated with a resource. And what happens is when a process uses the resource exclusively, when it locks it, it immediately gets a new priority attached to it. So this occurs as soon as the process locks the resource. And that new priority happens to be a priority level equal to the highest of all the processes that ever use that resource. All right, so let me repeat that. We've got resources in the system, all being used exclusively by processes. And with each of the resources, we associate a priority, and that priority happens to be equal to the highest priority of all the processes that ever use that particular resource. And now, when a process locks that resource, as soon as it gets it, it immediately gets that high priority. It doesn't wait, as is the case for the inheritance protocol, it doesn't wait until it starts doing blocking before its priority gets changed. It gets the new priority as soon as it accesses this shared resource. So low priority processes get automatically an immediately elevated priority. So that's how this one works. What occurs here is that at time t equals 1, little black arrow there is not pointing in quite the right spot, should be pointing right there. At time t equals 1, process A is locking a resource, which we know that process D is going to want. And because process D is the highest priority process that ever uses that particular resource, A immediately gets D's priority, just while it uses the resource. And then it unlocks it here, it gets its original priority back. Okay? So, rather than wait until the process starts blocking, which is what happens with the inheritance protocol, then we change the priority. We precede that, in this case, by immediately elevating the priority of the process as soon as it gets at the resource that we know that some other high priority process might also want to use. And that's how that one works. And like I say, I'm not sure whether that one's used in commercially available real-time operating systems. It might be, but certainly the inheritance, priority inheritance schemes is certainly used. All right. So we won't have any calculation style problems to solve with this particular topic. But what the takeaway messages for this stuff is we understand why dynamic scheduling policies are in some ways not favoured over static ones, because we're forfeiting that determinacy that we get, the predictability that we get from the static system. However, if we're prepared to forfeit some of that, what we can get is not only a way to model the blocking factors, but a way to reduce the severity of their impact by using inheritance and the ceiling protocol. So, in a couple of sentences, if you can explain those things, then that's good. Who's got some questions? All right. They're not difficult to deal with. This one's obviously easier to understand than that one, but nevertheless, neither of them are really rocket science. When you think about what it is that's going on, it does make sense. and useful. All right. So those are the last two canonical topics. As long as everyone can do the extended rate electronic analysis problems that we've got in here, then yes, there we are. Then I'll be happy. But can everyone do question 43? We've got a bunch of tasks. One of them's periodic. The top priority one is periodic. Another one periodic. One that's interrupt driven. What's that telling us? Blocking factor. As soon as we see the word interrupt, we think blocking factor. Correct. Another periodic process. Another blocking factor, and an aperiodic task down the bottom here. It says for the aperiodic task, it takes 30 milliseconds to compute every 300 to 500 milliseconds. So what are we going to do about the period for that aperiodic task? We're going to use worst case. All right, well, what is the expression going to look like for the schedulability of task A? What's its preemption factor going to look like? 0. It's the highest priority task in the system, so it never has a preemption factor. What's its task execution factor look like? Yep, 6/80, CA over TA. And does it have any blocking factor? Yes, in fact it has two terms to make a blocking factor. CC plus CEI over TA. That makes sense? Where did I get that from? Yeah, that's right. Yeah. So the execution time for task C will appear as blocking factor to higher priority tasks, as will the interrupt-driven part of task E. All right, what will the schedulability test for task B look like? I'm not worried about plugging in the numbers. Oh, wait a minute. What should be on the right-hand side of the inequality there? U of 1. 1. Yeah, that's right. Okay, what about the expression for task B? So there's a preemption factor. What's that? Yep, that's that. CA over TA plus CB over TB plus the same blocking factor that we have for the previous one as a function of task C's period. As a function of task B's period. Yeah. So we'll have CC plus CEI over TB. Must be less than or equal to U of 2. All right, what about task C? I'll do the easy bit. CA over TA plus CD over TB plus Yep. There's the task down execution factor, CC over TC. That's correct. And then there's a blocking factor, which is this over that. Yeah. That makes sense? No? Oh, yeah, very good. All right, so what's our test for task C? The whole thing is interrupt driven? CC over CC must be less than or equal to. Yeah. Must be less than or equal to 1. So we've got a requirement that the execution time for this task be less than the period plus this blocking factor. That must be less than or equal to 1. Not u of 3, 1. Why is it 1 and not u of 3? Yeah. It's an interrupted routine, which means it's being scheduled by the hardware. It doesn't care about what operating system is running, let alone what scheduler. And the u of whatever only applies to tasks which are being managed by a rate monotonic scheduler. So none of that makes any relevance at all in terms of the world as this particular task C sees it. It's simply got its own execution time plus a blocking factor to accommodate within the term period. All right. What about task D? Preemption factor. All the 3 higher priority tasks. CA over TA plus CB over TB plus CC over TC. Plus task D's own execution factor, CD over TD, plus the blocking factor, CEI over TD. Must be less than or equal to U of 4, yeah. That's right. What about this? Task D, does it have a blocking factor? No, it doesn't. Why not? Because even though this thing up here is interrupt driven, as far as task E is concerned, task C, whether it's interrupt driven or not, just looks like any other high priority task. It'll run whenever it wants to. So task C, even though it appears as a blocking factor to tasks A and B, from task E's perspective, task C just looks like some other high priority task. So the world as task E sees it is, whenever it wants to run, any of these higher priority processes might want to run, so all of those are preemption factors. And then there's its own execution factor, which is the sum of these divided by that, must be less than or equal to U of 5. And then the last one, quite straightforward. Every other task in the system is higher priority than the last task, so they all appear as preemption factors. No blocking factors. Blocking factors only have an impact upwards, not downwards. And so all we need to do is to see whether or not task F can accommodate its own execution time within the minimum period and all of these preemption factors as well. And that's it. And as the question says down here, and I mentioned this last week when we were working through the homework problems, writing down the algebraic expressions is what I recommend you do, even though it takes an extra couple of minutes. Because that way I can tell you know what you're talking about. You just start writing down numbers and some of them are wrong. I can't be sure that you really just made a simple arithmetic mistake, or whether you didn't have a clue. So, writing down some form of algebraic notation to indicate you understand the execution, preemption, and blocking factors, where there are any, that's going to get you the marks. well, we'll do the deadline electronic ones next week. They're pretty straightforward. You probably do those before then. The first one just asks us to use the imprecise test. And we've got 3 tasks here, so that's not too difficult to do. This one down here says that someone's already used the imprecise test and discovered that task C fails the imprecise test, but tasks A and B pass the imprecise test. So the question says, apply the more precise test to task C just on its own. Not all the others. But every semester there's 1 or 2 courageous students who see a question like this in the exam and go ahead and apply the more precise expression for interference factor to all 3 tasks, which is admirable, but a complete and utter waste of time. So don't do that. If the question asks for the more precise test to be applied to a particular task, then that's all you need to do. All right. So, next week, come armed and ready to mop up tutorial problems that you haven't looked at yet, the ones we haven't dealt with, and we'll spend whatever time necessary to do that in the class, and then that's it. You'll have everything you need for the second exam. So I think that'll do us for